Hey there, it's Shannon MATHCHICK Myers, and today we're checking out plane curves and parametric equations. So here we go, the slope of a line tangent to a plane curve. This is a kind of an interesting derivation, so I'm going to add a page so that you can see it. So we know that we have x is equal to f at t and y is equal to some g at t for the parametric equations. So if we're thinking about the slope of our curve c at x comma y, you start out with thinking about dy dx. But let's just sort of take a look. I mean, what is this? This is d dx of y. And now if we play around with the differentials a little, we still have this y here, but if we put the dx over here, and then we've got a dt in there, all right, then we end up with dy dt times dt dx. Now we want things in terms of dt, so we could write this as dy dt over the reciprocal of dt dx, which is dx dt. And guess what? That is exactly what the slope is, provided that dx dt is not equal to 0. Now, since we're here, we might as well go on to the second derivative. So you do a similar thing with the derivation. So now we have our dy dx, and we know that our dy dx is dy dt over dx dt. So again, we are looking for d dx of what we found for dy dx, which was dy dt over dx dt. Cool so far? Awesome. And now, if you, again, rewrite this, it's very similar to the last one. Again, we're going to multiply by 1 in the form of dt over dt. So then we'll get d dt, and now we'll switch this back to dy dx, and then divided by the reciprocal of dt dx, which is dx dt. Groovy? So again, we don't want dx dt to be equal to 0. And now we're good to go. So let's come on back here. If a smooth curve C is given by the equations x equals f at t and y equals g at t, then the slope of C at xy is equal to dy dx, which we found was dy dt over dx dt, and then the caveat that dx dt is not equal to 0. Groovy? Okay, so let's look at an example. X is 4 cosine t and y is 2 sine t on the open interval from 0 to 2 pi, non-inclusive. So let's find dy dx. We know that dy dx is equal to dy dt over dx dt. And so we will get dy dt. So remember, y is 2 times sine at t. So that's just going to be 2 times cosine at t. And dx dt will be negative 4 times sine at t. Now, this can be written as negative 1/2 times cotangent at t. Cool, cool? Now, finding the next derivative, we'll have d squared y over dx squared. Remember, that was equal to d dt of dy dx, which we found in the last one, over dx dt. That in turn will be, so our result last time had been negative 1/2 times cotangent at t, and so we'll get negative 1/2 times negative cosecant squared at t becomes positive 1/2 cosecant squared at t over dx dt is still negative 4 times sine at t. And at the end of the day, we will have negative 1/8 times cosecant cubed at t. Groovy? All right, beautiful. Now, there's our derivations, and let's go on to the next. Find all points, if any, of horizontal and vertical tangency to the curve. So up here, I'm going to just write what our dy dx was, and so that I'm going to write it before we simplified it to the cotangent function. So if you remember, that was 2 cosine t over negative 4 times sine at t. So how do I get a zero slope? That's for horizontal tangency. So if we do the first one, sorry, that's my dog. Horizontal tangency, we need a zero slope. And so we set 2 times cosine at t equal to 0 and solve. Cosine at t would be 0. So t would be pi over 2 and 3 pi over 2 in that open interval from 0 to 2 pi. Now, we are supposed to find the points where this happens, right? So if you recall, x was originally 4 cosine t, and y was equal to 2 times, what was it, sine at t. And so x will equal to 4 times cosine at pi over 2, which is 0. So we'll have the ordered pair, the first part of the ordered pair is 0. Y equal to 2 times sine at pi over 2 is equal to 2. So we got our first order pair, and this was at t equal to pi over 2, at t equal to 3 pi over 2, x will be equal to 4 times cosine at 3 pi over 2, which is equal to 0, and y will equal to 2 sine at 3 pi over 2, which will give us negative 2. And so, in conclusion, at 0, 2, and 0, negative 2, the plane curve has horizontal tangents. Good so far? Awesome. All right, now the other way we do this is we set, and this will be for vertical tangency, we would set dx dt equal to 0. And so remember that dx dt was negative 4 times sine at t, setting that equal to 0. We get sine at t is 0. So t would normally be, I'm not sure if I made a typo on the problem or not, but normally we would say 0 and pi, right? But 0 is not included in our interval for whatever reason, so we'll go with that. And so that means we'll have at t equals pi, we'll get x equals 4 times cosine at pi, which will be negative 4, and y will equal to 2 times sine at pi, which is 0. So at negative 4, 0, the plane curve has vertical tangents, has a vertical tangent. Now, if that 0 had been included, we would have had 2 points, which I kind of suspect normally it would be, but that's okay. We'll go with the open interval. All right. So next up, determine the open t intervals on which the curve is concave downward or concave upward. And so on this one, we want to use that second derivative and find the zeros of the second derivative. So if you recall, d squared y over dx squared was equal to negative 1/8 times cosecant cubed at t. Setting that equal to 0, we'll have negative 1 over, I'm going to write it as sine cubed at t, and then we would still have an 8 down here. And so basically this would give us 0 is negative 1, which is a contradiction. So there's no zeros. Of the second derivative. But the plane curve has vertical tangents at t equals 0, which we didn't include on the last one, and t equals pi. So we can use those to make our number line. Our number line goes from 0 to 2 pi non-inclusive, and then we had this vertical tangent line at t equals pi. And so we will have the interval from 0 to pi and pi to 2 pi. And we just need to find a test value in there. So we'll go with pi over 2 and 3 pi over 2. We're testing these values in the second derivative. So d squared y over dx squared at t equal to pi over 2 is going to yield negative 1/8 times 1 cubed, which is negative 1/8, no, Kuma, come out of there. Good boy. Good out. Good boy. And that is less than 0. And the second derivative, evaluated at t equals 3 pi over 2, is equal to negative 1/8 times negative 1 cubed, which will be positive 1/8, which is greater than 0. So, in discussion of concavity, we can say the plane curve is concave downward on 0 to pi and concave upward on pi to 2 pi. Cool so far? Excellent. All right. And so if you take a look at the graph, we'll go into parametric mode. And that first equation was x equals 4 cosine t and then we had 2 times sine t and let's see what it looks like. Okay, so when I just plugged in t equal to 0, and when t is 0, x is 4 and y is 0. And so this is how the orientation will go. So I'll just double check to see which direction we're going. And if we go to t equal to pi over 2, isn't that like 1.57-ish? Then we're up higher, so that you can see where the circle went from there. So our orientation, I'll click off of that so we can draw in our orientation, and paste the graph. Perfect amount of space for once. And so it started here and went this direction. Groovy? Some sauce. All right, so let's see what's next on the agenda here. Arc length in parametric form. So if a smooth curve C is given by the equations x equals some f of t and y equals some g at t, such that C does not intersect itself on the interval a less than or equal to t less than or equal to b, except possibly at the endpoints, then the arc length lowercase s of C over the interval is given by s equals the integral from a to b of the square root of dx dt squared plus dy dt squared with respect to t. You could also write this as s equals the integral from a to b of the square root of f prime at t squared plus g prime at t squared, if you'd like, with respect to t. Now make sure that the arc length is traced only once on the interval. So find the arc length of the curve given by the equations x equals arcsine at t and y equals natural log of the square root of quantity 1 minus t squared on the interval from 0 to 1/2 inclusive. All right, so here we go. First, let's find all the stuff we need to find. All right, so we need to find dx dt, right? Dx dt, and we're going to square it because that's what we need. So the derivative is going to be 1 over the square root of 1 minus t squared, and then we're going to square that. So that will just be equal to 1 over 1 minus t squared. And then dy dt, the quantity squared, I can rewrite y as 1/2 times natural log at 1 minus t squared. And so when I write the derivative, I will get 1/2 times negative 2t over 1 minus t squared. And then I'm going to be squaring that result. So that will end up being, when I divide out the 2's, the negative will go away, and we'll have t squared over quantity 1 minus t squared squared. So when I add these two together, all right, I need to get a common denominator, so I'll need to multiply this one by 1 minus t squared over 1 minus t squared. And so we'll get 1 minus t squared plus t squared all over 1 minus t squared, the quantity squared, which ends up zeroing out the t squared. So we'll get 1 over 1 minus t squared squared. Groovy? Okay, so that, of course, could take on a positive or negative with the integral. So basically, you can either write absolute value of that integral, or you can just remember if you get the negative result, you swap it to positive because arc length is positive. And the reason we'll get a plus or minus is because, if you recall, the formula also involved a square root. So the square root of our result is equal to plus or minus 1 over 1 minus t squared. Cool, cool? Okay, so here we go. This one, unfortunately, or fortunately, depending on your perspective, requires trig substitution. So here we go. We are working, our original integral will be s equals the integral from 0 to 1/2, and I'll need to check that it doesn't overlap itself. And then we'll have 1 over 1 minus t squared with respect to t. So let's look at the graphing calculator and make sure that it doesn't overlap itself. Going back to y equals, we have x is equal to arc sine at t, and then y was equal to the square root of 1 minus t squared. And I'll delete the other stuff from the last problem. Cool, cool? All right, excellent. So then when we graph, we'll have this little arc here, and let's just see where it goes from. So here, this is when t, it looks like when t is 0, t is 0.5 right here. And so I'm looking down at the bottom right, and it says 0.5, and so it doesn't cross itself on that arc, all right? And so I'll go back to the problem at hand, and then when we do our trig substitution, I'm going to add a page in here. Oh, I already had it added. Look at that. When I go to this page to do the integral, we make the substitution t equals 1 times sine theta. So t over 1 is equal to sine theta. And you make your triangle. This would be theta. It would be side opposite over hypotenuse, which makes this length square root of 1 minus t squared. Now I know there's no square root there, all right? So we'll be squaring that result because of what we have. Next up, what else are we going to need? We're going to need to know dt. dt is equal to cosine theta, d theta. And then we will have, just in case, if t is sine theta, theta would be arc sine at t. And the square root, actually I'm going to write it as 1 minus t squared is equal to the square root of 1 minus t squared squared, which would be the square root of 1 minus sine squared at theta squared, which will be the square root of cosine squared theta squared, which is just cosine squared at theta. Groovy? Okay, so now the indefinite integral, will be, we had 1 over 1 minus t squared dt. That is equal to the integral of 1 over cosine squared theta, and then dt was cosine theta d theta. So one of the cosine factors divides out from the denominator, and so we end up with the integral of secant theta d theta, which is the natural log of absolute secant theta plus tangent theta. I won't put the plus c because we're going to do a definite integral. And then using the triangle, we'll have the natural log of absolute secant theta will be 1 over the square root of 1 minus t squared, plus tangent theta, which will be t over the square root 1 minus t squared. So we can add those fractions because they have a common denominator. So we get 1 plus t over the square root of 1 minus t squared. Groovy? Okay, so now we will bring this back over here. So s will equal to natural log absolute 1 plus t over the square root of 1 minus t squared. And that's evaluated from t is 0 to t is 1/2. And so we will have s equals natural log. When I plug in 1/2, I'll have natural log absolute 1 plus 1/2 over the square root of 1 minus 1/4, because 1/2 squared is 1/4. And then I'll subtract from that natural log of 1 plus 0 over the square root of 1 minus 0 squared, which is just natural log at 1, which is 0. And so s will equal to natural log of absolute 3/2 over root 3 over 2 minus natural log absolute 1, which we said was 0. So we'll get, these 2's will divide out. 3 over root 3, when you rationalize, is equal to just root 3. So we get natural log root 3 linear units. Groovy? And we're done with that one. Awesome sauce. Little trig substitution in our life. All right, now we go to the area of a surface of revolution. So if a smooth curve C is given by the equations x equals f at t and y equals g at t, such that C does not intersect itself on the interval a less than or equal to t less than or equal to b, then the area S of the surface of revolution formed by revolving C about the coordinate axes is given by. So if it's about the x-axis where you have a g at t that's positive or 0, then capital S, you get the 2 pi from the revolving and the integral from a to b of g at t times what you had for the arc length. So remember, arc length was dx dt squared, all under a square root, times dy dt squared with respect to t. Now, if you revolve about the y-axis and you have an f at t greater than or equal to 0, we'll have capital S equals 2 pi times the integral from a to b of f at t times the square root of dx dt squared plus dy dt squared with respect to t. So for our example, we want to find the area of the surface generated by revolving the curve given by the equations x is 5 cosine theta and y is 5 sine theta on the interval from 0 to pi inclusive about the y-axis. So we'll use that second formula, and let's take a look at the graph. So we'll quit out of this one. We'll go back to our y equals, and I believe the first one was 5 cosine theta. We'll just use t in this case. The second one is 5 sine theta. Again, using t on this calculator. And we'll graph. And there we go, beautiful circle. Radius is 5, and the center is at the origin. Groovy. And then let's see, on the interval from 0 to pi, so let's take a look at t. When t is 0, you can see where we're starting. And then as we increase, t is now 0.88. So I think it's going to be here. Yes, when t is pi, it's that top half of that circle. Groovy? Okay, so we've got this circle here, and we're interested in this top half of it. But we have to be careful, right? Because we're going about the y-axis. So this bottom half isn't going to be part of the scene here, right? So I'm just going to kind of darken this one. And if you're revolving about that y-axis, you don't want to include this portion on your arc, okay? So we're going to have to stop this at pi over 2 to get our area. So we're going to be working on just this arc, and we're going to be revolving it. So it will, show up kind of as a trace here, or, and then you're going to get kind of like a dome, right? As you revolve about that axis. All right, so I'm not an artist. That's why I'm in math, okay? But here you go. This will be the surface, kind of like a gumdrop, okay? And this was our axis of revolution. Groovy? So, gave us lots of information. We need to go from 0 to pi over 2, right? And so let's see what all we've got going on. So S will equal to 2 pi times the square root of, and this will be the integral from 0 to pi over 2. And then actually our square root isn't first. F at t is first, and f at t is 5 cosine theta. So we'll have 5 cosine theta times the square root of 5 cosine theta, the quantity squared, plus 5 sine theta, the quantity squared, d theta. Good so far? Awesome. So S will be 2 pi, we'll simplify now, times the integral from 0 to pi over 2 of 5 cosine theta times, this will end up being 25 cosine squared theta plus 25 sine squared theta. This is looking good with respect to theta. And so S will be equal to 2 pi times the integral from 0 to pi over 2 of 5 cosine theta times the square root of 25 times cosine squared theta plus sine squared theta with respect to theta. And remember that cosine squared theta plus sine squared theta equals what? Awesome. That's going to equal to 1. And so we just have the square root of 25, which is 5. So if we pull out that 125, 5 times 5 is 25, times 2 pi is going to be 50 pi. And then the integral from 0 to pi over 2 of cosine theta d theta. So when we evaluate that integral, we're going to get 50 pi times sine theta, evaluated from 0 to pi over 2, which will give us S equals 50 pi times sine pi over 2 is 1, sine 0 is 0, and so S will equal to 50 pi square units because it's a surface area. Groovy? Awesome sauce. All right, so I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, click on that like button, share the video, subscribe to my channel, and I'll see you next time. Bye.